Welcome to The Explainer. Today, we're going to connect the dots between that tiny static shock you get from a sweater and, well, one of nature's most spectacular and powerful displays, a bolt of lightning.
I mean, for thousands of years, we've all looked up at the sky in awe. And let's be honest, maybe with a little bit of fear, just wondering, what is that? What is a bolt of lightning, really?
But here's the crazy part. What if the answer to that huge cosmic mystery is actually hiding in something as simple as, taking off a wool sweater in the dark and seeing those little sparks? The connection is there, but believe me, it took us a surprisingly long time to figure it out. In fact, it took over 2,000 years. The whole journey starts way back in 600 BC, with the ancient Greeks noticing that amber, when you rub it, attracts stuff. But it wasn't until 1752 that Benjamin Franklin finally proved that the spark from your clothes and the lightning in the sky were the exact same thing. Okay, let's dive into this.
So, to really solve this lightning mystery, we first need to shrink way, way down and get a handle on the fundamental forces at play, the actual building blocks of what we call electricity.
It all starts with something called electric charge. It's the super basic property of matter. And objects get it just through simple friction, like running a plastic comb through your hair or rubbing a balloon on your sweater. When you do that, those objects become charged.
And these charges, they follow one simple, universal rule that just governs everything they do. Opposites attract and like charges repel. That's it. That's the whole rule.
And you can see this for yourself super easily. If you charge two balloons the same way, they'll actually push each other apart. Same thing if you do it with two plastic pen refills. But bring a charged balloon near a charged pen refill and whoop, they pull right towards each other. That just proves they have opposite types of charge.
Okay, so far we've only been talking about static charges that pretty much stay put. But the real magic, the part that powers our entire world, and creates lightning, that happens when these charges start to move.
And that movement, that flow of charges from one place to another, that's what we call an electric current. It's basically the difference between a balloon just sticking to a wall and a light bulb actually turning on.
But here's the thing. These charges can't just flow through anything they want. Some materials, called conductors, let them pass right through. Others, called insulators, block them completely. And this shows it perfectly. You run a circuit through a piece of wood, an insulator, and nothing happens. But swap that wood out for a piece of metal, a conductor, and bam, the bulb lights right up. So generally, metals like copper and iron are fantastic conductors. They're like superhighways for electricity. Same goes for liquids that have salts in them, like your regular tap water. But on the other hand, stuff like plastic, rubber, and pure distilled water are great insulators. They just stop the flow cold. The material itself makes all the difference.
All right, now this is where things get really interesting. A flowing current doesn't just light up a bulb or give you a little shock. It has this hidden, transformative power. It can actually cause chemical reactions. When you pass an electric current through certain liquids that can conduct, it can literally break the molecules in that liquid apart. It triggers these powerful chemical changes. The whole process is called electrolysis. The classic example of this is splitting water. You pass a current through H2O and it breaks down into its basic parts. You can literally see it happen. Bubbles of oxygen gas start forming on the positive terminal and bubbles of hydrogen gas show up on the negative one.
So this chemical trick isn't just a cool science experiment. What's really fascinating is how we've learned to harness this effect for some incredibly practical and sometimes even beautiful things. This leads us straight to a process called electroplating. And at its core, it's just a technique that uses a carefully controlled electric current to coat an object with a thin, perfect layer of a different metal.
The whole thing is like this controlled, microscopic construction project. The electric current basically persuades metal atoms to leave one place, travel through a special solution, and then perfectly reassemble themselves atom by atom onto the object you want to coat. And once you know what it is, you see the results of this everywhere. It's what gives car parts and bike handlebars that shiny, rust-proof chrome finish. Jewelers use it to plate things with gold or silver. Even the tin cans that keep our food fresh are made by electroplating a super thin, protective layer of tin onto steel. Okay, so let's recap. We've seen how charges attract and repel. We know they can flow as a current. And we know that current can actually change matter itself. Now, we finally have all the pieces we need to solve our big mystery.
Lightning is born from these exact same principles, just on an absolutely epic scale.
Inside a storm cloud, all the violent movement of air and water droplets rubs them together, creating a huge separation of charge. You get positive charges way up at the top of the cloud and negative charges pooling at the bottom. When that imbalance gets so enormous, the air, which is normally an insulator, remember? It just can't hold it back anymore, and a massive electric current, a discharge, flows to even things out. That is lightning.
So think about that for a second. That blinding bolt of lightning and the tiny little static zap you get from a doorknob. They are, fundamentally, the exact same thing. They're both just electric sparks. One is just on an awesome, terrifyingly huge scale.
So from the almost invisible pull of a piece of paper to a calm, all the way up to the sky-splitting power of a thunderstorm, the very same basic rules of electric charge are at work, running our world in ways we can see and in ways we can't. That really makes you wonder, doesn't it? If the same simple rules can explain both a tiny spark and a massive storm, what other invisible forces and incredible connections are out there just waiting for us to figure them out?